All right, good morning, welcome. Any more submissions for the homework assignment? Thank you. All right, so looking into the future, on Thursday you'll have your first quiz of the semester. That's covering the first two problem-solving assignments, not including the getting to know you assignment. So lectures 1 through 5, including today's class lecture. I haven't written the quiz yet, so I can't tell you exactly how many questions it'll be, but usually what I like to do is have it be so that it takes only 15 or at most 20 minutes during the class time so that we still have plenty of time for the new material that day. So it'll give you a glimpse of the style of questions I ask for exams because these quiz questions are about the same level of difficulty and the same length as an exam question. It's just that during exams you'd have 3 or 4 of these questions instead of a single one. So that'll be on Thursday in class at the beginning of class. And then a week from today, homework 3A is due. And it's, as you can see, a lengthy assignment. Lots of problems. No single one of them is especially complex. It's just we're covering a lot of different types of applications. And so I'd encourage you to get an early start on that. I'll give you some key ideas at the end of today's class lecture on a few of these problems. And then, of course, some of those problems are related to material you won't hear until Thursday, but that doesn't mean you have to wait until Thursday to begin the assignment. You could do the first half of the assignment after today's class, and I'd encourage you to get an early start. Any questions related to the announcements or anything else? Yeah. That's right. Yeah, on the quizzes I'll provide the formulas so you don't need to memorize them or write them down. Although I bet many of you already have the hydrostatic equation memorized. Right? It's just sort of natural. Right. There are a few things that I wouldn't provide. For example, the unit weight of water, that's something I expect you to know, right? Or the density of water. A couple of physical constants we're going to use a lot this semester, so that should just always be at the tip of your tongue. Anything else? Yes?
So for the unit weight,
yeah, the SI units. You don't have to memorize the traditional units. The standard default, which is 9810, and that's not at 20. That's actually at between 4 and 10 degrees Celsius. At 20 is 9790. But the one I expect you to just sort of use unless another temperature is specified is 9810 or the density of 1000. All right, so this is where we left off last time, talking about the hydrostatic equation. And I know it was a long weekend, a 3-day weekend. Maybe you burned through all of your memories of last Thursday's lecture. So let's just refresh our memories how to do problems like this. There's the full hydrostatic equation where we pick 2 points and we find the pressure based on those 2 points, or the abbreviated approach, which is just to look at a difference in pressure as a function of some delta H, which is a difference in depth. So what I'd like you to do is assume that this tank of liquid, water, this tank of water, we have location 1 is at the surface of the water, and we can say that gauge pressure at the surface of the tank is 0. And we would like to know what is the pressure at location 2, which is 35 meters under the surface. And so just to refresh your memory, solve for this both ways, where you substitute an actual value for P1, Z1, P2, Z2. You'll be solving for P2 in this one. And then the abbreviated approach where you're just using a delta H. Right, so what do we know? We know the unit weight of the water. If no temperature is specified, we'll use 9810 newtons per meter cubed. We've got the Z values from the drawing. The pressure at 1 is 0 gauge or 101,325, which is the absolute pressure of atmospheric. So I asked you to solve this both ways. First with the hydrostatic equation. And so if you rearrange the hydrostatic equation just to isolate the unknown P2, then this is what we get. And And so we're multiplying essentially the unit weight by the difference in elevation, and where we're assuming that the pressure at 1 is 0, since that's gauge pressure. So that will tell us the gauge pressure at 2 is 343, 350 newtons per meter squared. And then if we want to know the absolute pressure there, then we just add on atmospheric on top of it. So it's the difference in measuring basis for the two different absolute versus gauge. This is just an example of the easiest possible question I can conceive of for a quiz. I'm not saying the quiz will be this easy, but it certainly won't be easier. The abbreviated hydrostatic equation, we're just using the delta P, and so we say at the top of the tank the pressure is 0, and so as we go down through the liquid the pressure is increasing. For every meter the pressure is going up 9810 pascals. So we multiply the depth by the unit weight, and we see the pressure increase is that same 343, 350, and then the absolute pressure, you're adding atmospheric on top of it. So we get the same answer either way. All right, any questions about this illustration? Review? All right. One of the principles that we know about pressure is that it's additive, and that pressure continues to increase regardless of how many different fluids that you have. And so what we have in this example is a situation where there's a layer of oil and a layer of water. And we know the unit weight, specific gravity of the oil is 0.75. Now I've already kind of given it away by the colors in this drawing that the oil's on top, but even if you didn't know it from the colors, it's sort of like an oily color. Just the specific fact, the fact that the specific gravity is 0.75 would tell you that it's floating on top of the water. So here's the water, here's the oil, we have SG is 0.75, and how can we use that SG? What does that enable us to calculate?
The oil gravity over water gravity.
Okay, good. So the definition of specific gravity would be the unit weight of oil divided by the unit weight of water. And so if we know that ratio, and if we also know the unit weight of water, which luckily we do because we memorized it, then we can find the unit weight of the oil, which we will use anytime we're doing hydrostatic calculations. All right, so we can find out what is the unit weight of the oil through this ratio. The unit weight of the water, we just sort of already know that one. Let's see, is it giving us a special temperature? 10 degrees Celsius. 10 degrees Celsius water. So I think I use 9810 for that one. It's not till we get to 20 that we'd use a different one. Yeah, 9810. All right. Unit weight of water. All right. And then the dimensions are a little tricky on this one too. It says that it is a 4-meter tank. So that's the total liquid level, inclusive of both of the fluids that are in there. And so 4 meters is the entire liquid level. And we have a layer of oil that's 1.1 meters thick. So this is 1.1 meters. Okay. So what I'd like you to do is find the pressure, the gauge pressure at the bottom of the tank. We want to know the pressure here. So it's applying the hydrostatic equation, and we're going to do it in 2 jumps. You go from location 1 to location 2, and then from location 2 to location 3. So essentially, you can't go all the way from 1 to 3 in a single step because there's 2 different liquids there with 2 different unit weights. We're going to be applying the hydrostatic equation, and you can't go all the way from the top of the tank to the bottom of the tank because what unit weight would you use? You maybe think, well, I can average the unit weight, or no, you can't do that. You have to do it in steps. So just apply it going from the pressure from 1 to 2, and then you'll find out the pressure at 2, and then the pressure at 3 is whatever the pressure at 2 was plus an additional increase in pressure between the 2 points. All right, so I'm going to pause the recording and give you a few moments to calculate the gauge pressure at the bottom of the tank. All right, so I'll keep harping on the fact that it really is helpful for you to do a sketch, even if you're looking at one right in front of you. Something about doing the drawing yourself makes the problem more clear. You'll notice that I labeled the locations where there's an interface between a gas and a liquid, which is location 1. Location 2 is when there's the water-oil interface, and then 3 is the interface of the water and the container. It's the vertical distance only that really determines the pressure change, and so they don't have to be right on top of each other like they are 1, 2, 3. I could have had number 3 labeled over here off to the side, and it doesn't affect the pressure at all. It's only vertical distance through a fluid that accumulates pressure, not side-to-side distance. All right, so we're asking the pressure at the bottom of the tank, and just even if you don't know how to solve a problem, anytime you're given the specific gravity of a fluid, you should automatically say, well, probably I should use that specific gravity to find out what's the unit weight or the density of the fluid. Just kind of getting the preliminaries out of the way and preparing the information you're going to need for the rest of the problem. So that's the first thing I've done here, is just calculated the unit weight of the oil based on the specific gravity that was given. And then the way that I've thought of it after that is you start at 0 where you know the pressure. So in problems like this, and we'll get some pretty complicated manometer problems, you start where you know something and you work towards the unknown. And that's like a physical, literal thing. Like when I say working towards the unknown, there will be a location where you don't know the pressure, and so you're going to either be going up or down through a fluid. And anytime you're going down through the fluid, the pressure is increasing. Anytime you go upward through a fluid, the pressure is decreasing, and it does that at the rate of the unit weight of whatever the fluid is. So in this case, we're first going from 1, where we know the pressure is 0, towards 2. And so the pressure at 2 is going to be whatever the pressure at 1 was plus the change. And plus is because we are going downward through the fluid. So the pressure at 1 was 0, and then we have 1.1 meters of pressure as a result of going down through that oil. So we multiply it by the unit weight, find the pressure at 2. And now the pressure at 3 is whatever the pressure at 2 was plus the change. And the change again is positive because we're going downward through the fluid. This time though, there's a different unit weight since we're using water between the 2 interfaces, and then multiplying it by the different height, which is 2.9 meters. And don't let the tricky dimension, the way the dimensions are described, throw you off. You know, where it's saying it's 4 meters tall from the bottom of the tank to the top of the oil, and then they tell you 1.1 meters is the oil length, so obviously you have to subtract 1.1 from 4 to find the thickness of the water layer. And sometimes in your homework problems, it'll be the same kind of thing where they're being maybe a little bit obscure about the way that a drawing is dimensioned or the way the givens are supplied. Any questions from this example? Okay. So here's what we're going to talk about for the rest of our class period. We're going to be talking about pressure transmission. And this is just kind of a schematic drawing that shows how a lift in a garage might work. You know, every lift is a little bit different, but this is just sort of a generalized representation of, not shown is some sort of an air compressor that's taking air from the surrounding area, putting it into this pipe, and then it's pressurizing the air above a reservoir of oil. And the reason for doing that is that when you pressurize the air that's above the oil, then the air is going to be pushing down on the oil at some pressure intensity. Okay, so We've pressurized the air and it's pushing down on the oil. Well, what happens to pressure as we go down through a fluid? Increases. All right, so the pressure is increasing, it's increasing. What about when we go sideways through this tube? What's happening to the pressure? No change. Okay, now we're going back up through the oil. The pressure is decreasing a little bit. I mean, there wasn't much of a change as we went down because we've pressurized above the oil reservoir pretty high. And so then you have some minimal increase in pressure, some minimal decrease. Well, the main point is that now, because these are at roughly the same height, the pressure pushing up on this cylinder is the same as whatever it was inside of this reservoir. And so the benefit of this is that we may want to pressurize the oil somewhere far away from where we're actually applying the pressure. We want the pressure inside this oil to be pushing up on the cylinder because that's what lifts the car, is the pressure that is in that oil. The weight of the car is in kilograms. No, the mass of the car is in kilograms. What's the weight of the car in? Newtons, all right. What are the units of the pressure inside of this oil? Newtons per meter squared, which is the same as pascals. Okay, so without having told you any sort of equation, if we have pressure, so this is our given, we know what the pressure is in here. We maybe have some sort of a gauge that's telling us what's the pressure in there. Okay, we know the pressure and we want to find out how much it's going to be lifting. So we've got pressure is this units. We've got the force, which is the units of the weight of the car. What do we have to do to the pressure to get units of force? Multiply it by some area. You can see that in the drawing there, it tells you that you have a diameter of 25 centimeters. So from that, you can find the cross-sectional area, talking about the area of that cylinder there. And so in a situation like this, it's a way of transmitting pressure from some off-site location to where you want it applied, and it can help you to find the force lifting up the car. And it's going to be in equilibrium. If it's not rising or falling, then the lifting force is equal to the weight of the car. In this example, it says that we have some diameter of 25 centimeters, and so from that we can calculate the area, because area is pi d squared divided by 4. So just applying that formula, we find the area, talking about the bottom area of that. And if the air pressure is 600 kilonewtons per meter squared, then we can find out how much it is lifting up the car. So here's a little sketch that illustrates that. We've got the air pressure down, which means that the hydraulic pressure is up. It's pushing on that cylinder, and that's with the force of about 29,000 newtons. So that works out to about 3,000 kilograms if we divide 29,454 newtons by 9.81 meters per second squared. Because remember, weight is mg, so mass is weight divided by g. All right, so this illustrates how you can use pressure transmission in kind of a useful way. But let me ask you this. What if we increased the pressure? Right now it's at 600 kilopascals. What would you expect to happen to the car if we turned on the compressor and started adding more pressure? All right. Yeah, so if we turn on the compressor, the force will increase because the pressure increased. We said force is pressure times area. So if you increase the pressure, then it's going to increase the force, and so it would lift up the car if you turn on the compressor. It's going to raise the car. It's not going to raise it forever. It's going to come into a new equilibrium. It's going to be a little bit higher than it was before, and that difference in elevation how much higher it is related to how much additional pressure we put in. You know, if we go from 600 kilopascals to 605 kilopascals, it'll have some increased delta H that is related to the delta P. We can use the hydrostatic equation to tell us how much higher it will rise as a function of what the unit weight of the oil is. We'd need to know the unit weight of the oil before we could say exactly how much higher it would get. But I think you understand the main principle, which is just that you increase the pressure, you're going to increase the lifting force. And the same thing is true is if you change the cylinder diameter. Right now the cylinder diameter is 25 centimeters, and so that's where we get the area from. What if we took it from 25 to 50 centimeters? What would happen in that case? For the same 600 kilonewton pressure, kilonewtons per meter squared. What if you doubled the diameter? Can it lift more, lift less, or lift the same amount? Okay, we've got some differing opinions. Some people say it'll lift less. Some people say you need to double the force. So let's say that we're keeping the pressure the same. Okay, so the pressure is the same, but when we double the area, when we double the diameter, what happens to the area? It's going to go up by a factor of 4 because we're going to be going from, instead of 25 centimeters, which is 0.25 meters, so instead of 0.25 meters squared, it's going to be 0.5 meters squared, and so it's going to be the area going up by a factor of 4. If you increase the area, you're going to increase the lifting force by a factor of 4 if the pressure is the same. So this is kind of, at first, a little bit of a mind-bending idea that to lift more, all you have to do is make that cylinder a bigger cross-sectional area. And you can lift progressively heavier and heavier loads. It's a principle of mechanical advantage. And we're going to see that in this next example, where we have a jack, a hydraulic jack like you maybe would use at your house to lift up a car when you're changing the tire or working on the brakes or something. Now this has mechanical advantage in 2 different ways. The first bit of mechanical advantage comes from the handle. The way that the handle's working is that you're pushing down at one point pretty far away from the pivot point. The handle is pivoting about location C. So let's just do a little sketch of the handle here. So we've got the handle, and here it is pivoting, and our distance from the pivot point to where the location of the force is 33 centimeters. All right. So it's 33 centimeters to where we're pushing down. And then when we push down, the reaction to that is we're trying to cause this plunger here to go down into the hydraulic fluid and pressurize the liquid that's inside of the jack. That's why we're pushing down on the handle, is so that we can create pressure inside of this reservoir. And so when we push down, what the handle is going to experience as we push down on the end of the handle is it's going to see that it's being pushed up on by that little plunger. And the plunger itself is going to be having a force that's downward because of us pressing on the handle. Okay, so what we're going to ultimately try and find out is what is F2? How much can we actually lift if we're able to apply a force of 100 newtons on the handle? And so the first thing we have to do is find the mechanical advantage that is arising because of the handle there. And that's just like a moment analysis. You know, force times distance equals force times distance, and it'll be in balance there. So your moment distance for the handle is 33 centimeters, and the moment distance for the plunger is 3 centimeters. All right, that's the first bit. Now, how do we find out what is the pressure inside the reservoir? Okay, good. Yeah, the forces are in equilibrium, so that means that the cylinder on the right isn't rising anymore. we can just use the same formula that we've already been applying. Force is pressure times area. Or if we rearrange that, pressure is force divided by area. So in the first part, what you're going to find out is what is the force that is pressing down on this plunger on the left, just based on the moment analysis about the handle. So you're going to find out what's this force, what should we call it? F on A1. That's the force that's applied on that object that's going over A1. Now, we're told that the diameter of this piece is 1.5 centimeters, and so we can calculate the cross-sectional area from that. So we'll have the force divided by the area of that piece, and that's what's pressurizing the liquid inside of this part, is the fact that we're pressing down with some force, and that force is being applied over a circular area. So now the fluid is pressurized, and then the fluid that's pressurized is acting upward on this other cylinder, and again we're applying F equals pressure times area. There's going to be a different area because this is a larger diameter cylinder. It's 5 centimeters instead of 1.5. And so we can find out what is F2 just by multiplying the pressure by the area of that cylinder. All right. So a few different steps. I'm going to pause the recording, circulate around if you've got questions, but the first place to start for this one is the moment analysis about C for the handle, to find out what force is pushing downward at area 1. Okay, so if we push down with 100 newtons on the left of that handle, then what it does, in order for this to be in equilibrium, there has to be a force up at B with a magnitude of 1100 newtons, just because of the distances and so on. So if it's pushing up on that handle with 1100 newtons, then that means it's also pushing down on that plunger at A1 with the same force. And then we can find out if you're using that force over a small area, like a relatively small area because it's just 1.5 centimeters, then that's going to pressurize the liquid inside of the reservoir. And so a force divided by the area will tell us the pressure of the hydraulic fluid. And then the pressure at A1, the pressure of the liquid at A1 is the same as the pressure over at this other spot because they're about the same elevation. And so then we have to calculate the area at 2 and multiply that area by the pressure of the liquid, and then that'll tell us the lifting force of how much the jack can lift. All right, so what are some other ways if we needed to lift more than that? What could you do if you needed to lift more than 12,000 newtons? Okay, so decrease the diameter on the left and increase it on the right. Yeah, changing the ratio, that's one of the force multipliers there. Yeah, make the handle longer, right? So that'd be another way of doing it. Or moving this one closer to C would be another way of increasing the force. Or pushing harder, I guess, is another way to lift more. Right. Good question. So he asked, what about increasing the column height? Right now, it looks like these are about the same elevation. So if you just made the column longer, then what you're doing really is adding to the weight of the system. We've kind of neglected the weight just by saying that it's in equilibrium without any force, and then we're going to apply some additional force here on the handle, and then that's why we can lift it too. But you know, the more we push, we're going to elevate this slightly, and so the hydrostatic equation would say that the pressures aren't exactly equal if you're lifting this up. If there's a deflection there, then, you know, the pressure was so high, this 6 megapascals in the solution, yeah, 6,225,000 pascals. Even if there was a elevation difference of, you know, a couple of centimeters, it's not going to have a very big decrease in the pressure. But just changing the physical height of this column isn't going to increase our ability to lift heavier things. But I'm glad you asked about that because, you know, so far in both of the examples we've worked, we've had the liquid levels being equal. But we can handle the fact that if the cylinder was up here, then we need to find the pressure there that's caused by how hard we're pushing on the jack, and then we need to know the pressure someplace else. We just apply the hydrostatic equation. It is the pressure there minus some change as a result of if it's being elevated above it. So we just apply the delta P is delta H times gamma. All right. So the way that we can measure pressure has evolved a lot in the last few hundred years. The oldest way that pressure was measured was with a device called a piezometer. And manometry in general is just a way to describe efforts to measure pressure. And so let's say, for example, that we have a water line going underneath the road, and we do. So envision that this is the water line that goes under the road. Now I've told you before that like a typical ballpark pressure of a water line is about 500 kilopascals, 500 kPa. So that's the same as 500,000 newtons per meter squared. If we puncture that pipe that's running under the road, well, water's going to be spraying everywhere. But if we puncture it and then we connect a tube that just goes upward, the water is going to rise up in that tube that we've connected until it gets to a certain height, h, that corresponds to how much pressure is inside of the pipe. And so in the case of approximately 500,000 newtons per meter squared, we divide that by 9810 newtons per meter cubed, which is the unit weight of water, and we're going to get roughly, what, about 50 meters, 50 plus meters. So what that means is if we wanted to have a piezometer to measure what's the pressure in pipes that's going under the road, we'd have to punch a hole through the pipe and have a tube going upward, and then it would rise the water level to about 50 meters, which is really, really tall. You can make stilts go pretty high, but not 50 meters high. So it's not really a practical way to measure pressure just because the height of the water column is so large. You know, another issue with piezometers such as this is that they can't be used to measure gases, not directly. Because if you have gas going through a pipe and you punch a hole in it, then the gas is just going to exit through the hole that you've punched. It doesn't, it's not restricted, the height isn't restricted in the same way that a liquid is. So manometry, the simplest way to measure the pressure inside of a pipe is just with the piezometer. And applying the hydrostatic equation where delta P is delta H times gamma, the unit weight of the fluid. Here, H, that's shown in the drawing, is what you'd put into a hydrostatic equation to know what's the pressure inside of the pipe. There are better ways, and we're going to talk about those better ways of measuring pressure in the coming class periods. But with the rest of our class time today, we're going to take a look at 3 of the problems that are on this really large, lengthy homework assignment you've got due a week from today. I want to kind of ease you into this by defining some of the terminology that maybe would cause a little bit of confusion otherwise. All right, on problem 315, I've abbreviated what the problem statement says. It says, as pictured, so what we're seeing right now, the air pressure in this enclosed section is 50 kPa vacuum. And because of that vacuum, water rises to H. As you can see, The water's getting sucked up into that tube. So what do you make of this 50 kPa vacuum? What do you?
Pressure is a negative gauge pressure.
Okay. So if we're saying that gauge is 0, then anytime we would have less than 0, that's either negative gauge pressure or vacuum, right? So we know that, according to the problem statement, atmospheric pressure is 100 kPa. So in the first case that's pictured, the air pressure inside of this enclosed space, it's 100 minus 50. So it's going to be 50 kPa inside of there. So there's an equation that allows you to find differences in elevation due to differences in height. You could say, let's have this be location 1, where the water is intersecting the atmosphere. So this is location 1. You could say, let's have this be location 2, where the water is touching the air inside that enclosed tube, and the pressure at 2 is 50 kilopascals. And then you're simply solving for the difference in z's. Remember, P1 divided by gamma plus Z1 is equal to P2 divided by gamma plus Z2. So the question is, what is H? Essentially, it's going to say there's a before and an after, and how much is the water height changing when the pressure is changing. It's a two-step problem, and the first step is apply the hydrostatic equation. Apply the hydrostatic equation where 1 is here, where you know something, you know the pressure, and let's say that our Z datum that you're going to be measuring elevation from is this water surface. And so you could say Z1 is equal to 0. You could say P1 is equal to 100 kPa. The unit weight for water, 9.79 kilonewtons per meter cubed. So you can find out for the P2 is 50 kPa because it's 100 kilopascals less than atmospheric. That's what vacuum means. Then you can find out what is the Z2. And by inspection, just by looking at it, we'd expect that the Z2 is going to be higher than Z1 was. It should be a positive number, not a negative number, because it's getting sucked up inside of that tube. So that's the first step, is to find out, as pictured, what is H. But then it goes on to say, what if this pressure is changed from 50 kilopascals, absolute. Now it's going to be changed to 25 kPa vacuum. Okay, so in the after, P1 is still atmospheric pressure, 100 kPa. What's P2 in the after? 25 less than this. So it's 25 vacuum, which is 75 kilopascals. So it's not just 25. You have to say 25 below 100 because the vacuum is saying less than the gauge pressure, which is atmospheric. So if you, this was at 50 kPa, the water was getting sucked up inside of the tube by a vacuum of 50 kPa. What is going to happen to H if we change it from a vacuum of 50 to a vacuum of 25? You think that H is going to go lower or is it going to go higher? Have a few votes for lower? Yeah, you're right. It's going to go lower because if you can think of it this way, it's not getting sucked up into the tube as hard. It's just like a straw, you know. How much water or soda goes into your mouth through the straw is dependent on the suction pressure. And so here, the suction is decreasing. The vacuum's going from a vacuum of 50 to a vacuum of 25. So H is going to decrease, but they want to know by how much. And so you have to find out what is H before, what is H after, and then find the difference between the two, because that is the decrease that the problem is asking for. All right, so are there any questions related to these key hints here?
says a vacuum, it needs to be subtracted from the atmosphere.
That's right. Other questions? Here's a problem similar to what we've been working on today. Look at the device. There is a container of oil. On top of that container is a piston, and then there's a weight on top of the piston. So that weight is going to be pressurizing the oil. Now, there's this other thing off to the side of it. What is this off to the side? What's the purpose of it, do you suppose?
That's to measure change in pressure.
Good. That's right. It's to measure the change in pressure. And so it's like the piezometer we were just talking about. It's open to the atmosphere. And so the difference in pressure from atmospheric, right here where the air is touching the oil, the pressure is 0. But then we go down through the fluid, and if we know H2, how could we calculate the pressure at that location? Just by multiplying the unit weight of the oil by H2. So remember the abbreviated version of the hydrostatic equation, which we've used before. Delta P is delta H times gamma. So here it's some oil, which we can find the unit weight for based on the specific gravity, or maybe they've just told us directly. So we can go one of two ways. We can either find out the pressure at this location by knowing H2, or in this problem, they're telling you the mass of that load. So from the mass, you can find the force by multiplying by G. And then if you know the force acting over a certain area, then that tells you the pressure of the liquid. And so you've got the piston diameter. And so pressure is force divided by area. You can find the pressure of the oil there. So what it works out to be is that from the stuff you know on the left, you're going to have some known pressure at the interface of the piston and the oil. And that will be the same pressure as over here on the right side. So you'll have a pressure known at the bottom of that H2 distance. You know the pressure at the top of the H2. And so you'll find the magnitude of H2 just by applying the hydrostatic equation. So in other words, just to summarize, delta P will be known. The unit weight is known because of the oil's specific gravity, and you'll be solving for delta H, which is the H2 that they want to know there. What about H1? How do you use that? You could, if you want to use the full version of the hydrostatic equation instead of the abbreviated, you could use that. Let's say the bottom of the container is your Z datum. So if you wanted to do that, you could. But actually, H1 is not needed. It's irrelevant information because you could solve it just based on the abbreviated hydrostatic equation. Now, this is something that you're actually going to start facing more and more often. In your engineering career, most of the information that people give you, it'll be irrelevant, especially when you're working with non-engineers. They're going to tell you so much stuff about their problems, dimensions that it's not relevant, problems that they've observed in the past, and so you should not get thrown off too much when you're given information that's not needed like this. The H1, it ends up, you can do all the calculations that you need without that. So, any questions about this problem? Let's look at one more. And this one's pretty tricky. So imagine that you have this part. And what it is, this is a hemisphere. And so it's like you've cut a ball in half. And it's like a metal dome that has water in it. And then there is a tube going up to the top some distance. Now you'll notice from the drawing here that it's got some bolts. And what would you suppose the purpose of those bolts is? Or another way to ask it is, if these bolts weren't here, what would happen to the water? Okay, it would lift up the container, and you're making a gesture. What is? Yeah, the water's just going to leak out the bottom, right? So you can just sort of envision the fact that if you want there to be a watertight seal, this is like this metal hemisphere is resting on a planar surface. So it's maybe like a table or something. The water is going to be leaking out the bottom unless you bolt it down or press down. And so what we can do is a force balance on the bottom of that surface that the water is pressing on. The container, the metal hemisphere, has a certain weight. We're told that this pipe and the dome that it's connected to has a weight of 6 kilonewtons, so that's acting downward. And the bolts are pulling this dome downward as well. And the weight of the water is itself also acting downward. But the table is pushing up on the water. There's a certain pressure at the bottom of that part. And you can find the pressure at the bottom of the part because we're given these distances L. So we're saying L is just some standard unit of measurement, 80 centimeters. So you can find the pressure at the bottom of this part because it's 7L to the top minus 1. So it looks like 6L from the open end of that tube to the bottom. So you can apply the hydrostatic equation. You can find the pressure at the bottom of the tank by delta H, which is going to be 6 times 80 centimeters. And then the unit weight, in this case, it's just water. So this is really a force balance problem. We can say all of the forces in the vertical direction will be in equilibrium. Overall, it's asking how much do the bolts have to pull down to hold the system in place. Okay, so what are the forces? The bolts are pulling down. The weight of the water is downward. The weight of the dome is downward. The only thing acting upwards is the effect of the hydrostatic force. So the water's pushing down on the table, and the table is pushing up on the system with the same pressure. So the net effect is an upward force, magnitude equal to the pressure at the bottom of the tank multiplied by the area at the bottom of the tank. And this is a circular shape. This hemisphere acting on a table, the bottom of the hemisphere is circular. So you can see that the radius of that circle is 2L. So that means the diameter of that circular shape will be 4L. This is a little bit tricky, and I think probably the part that's not immediately intuitive at first is that this force is acting up. It's what's causing you to need those bolts in the first place. I mean, you kind of know that the bolts have to be there, otherwise the water's going to leak out. And what reduces the force of the bolt that's required is how heavy this part itself is. And so that's part of it, the weight of the water, the weight of the dome. Both of those things decrease how much force is required in the bolts. But what's causing it in the first place is the pressure. And so the more pressure that exists at the bottom of this, the greater the risk is it's going to leak. So a high pressure at the bottom of the tank multiplied by the area is that force that's required to counteract. That's the upward force. Any questions about this one? Let's look at the announcements one last time. So what I'm saying, I just gave you the hints for up through 29. I think you can solve most of this assignment based on what we've gone over in class today, up through 29. I think we'll have time to look at least one or two of these next batch on Thursday, but I'd encourage you to get an early start, and I'll see you on Thursday for our quiz.